main results. So I hope you can hear me clearly.
Yes.
Yeah, good. If you cannot hear me, then just let me know. Okay, so we have this angular momentum operators. So our basic starting point is here, this commutation relations. And we talked about such a set of operators that fulfill this type of commutation relations as a form of Lie algebra. So this is an example or a particular form of Lie algebra, and we discussed that if we have such a Lie algebra, then we can regroup the operators into a set which mutually commute, and the rest which can be written as ladder operators. So that's the raising and lowering operators. So in our case, the case of angular momentum, the largest number of mutually commuting operators is 1, because if you take any two of these operators, they do not commute. Yes, so there is only one mutually commuting, and that we choose to be the JZ, the Z component. And then the rest, the JX and the JY, can indeed be written as ladder operators, as like in this case here. So that's just JX plus minus I JY. And if we do that, then we have this commutation relations, of course equivalent to this one here. It's just rewriting the operators in terms of JZ and J plus minus. So we have is the first one, which looks like a bit like an eigenvalue problem, but for operators instead of for states. So you have an eigenvalue of plus and minus h bar. And we can see that we have a state Gm like this, and we operate it both sides. So we get M like that, and we can easily work out that J plus minus acting on the eigen state Jm will give us M, I think, plus minus 1 H bar. M like this. So you can see that this state is also an eigenstate of Jz, but with eigenvalue M plus minus 1. So that's why it is called lowering and raising operators. And then we also know from general consideration that we can form an operator that commutes with all the operators in the set. So that's the J squared, usually called the Casimir operator. So that's a short summary of the angular metal operators. And then we showed that this angular momentum operator is the generator of rotation. So we showed that for the case of L, so that's the angular momentum in real space. So we operate that on the position eigenstate, then we verified that it does indeed rotate the state. Then we say we generalize this to include rotations also in spin space. So the J here can be element L, but can also be a spin as and maybe some other operators that behave like angular momentum. So this is the basic expression for the rotation operator. So this is an operator that acts on a Hilbert space. So the rotation itself is given by this here. So let me call it R. So that is the rotation in three-dimensional space. So sometimes we talked about induced rotation in the sense that the rotation itself is done in real space, of course. So this is represented by R. So that's a rotation along a given axis n and by angle phi. But the rotation operator acts on a Hilbert space on some states. So that states can be well, can be anything, can be spin states, for example. So this gives them the connection between the rotation in real space and the rotation in the Hilbert space. So if we look at the effect of rotation on the wave function, and this is, you can see here, so we have a state psi, and we rotate it. Then if we look at projections of this rotated state in position representation, then it is just the same as the original wave function. I should say wave function, not state here. So it's a wave function, but with the coordinate rotated. So we can think of it in two ways. Either we think of it as the coordinate being rotated, coordinate system being rotated, or that the wave function itself is rotated in space. So this R is just an orthogonal matrix that represents rotation in 3 dimensions. I see. Okay, so maybe I should do it like this. It's better. Yes, more stable. Can you hear me now clearly? Yeah.
Yep.
Yeah, good. Yeah. So I was saying that in the case of wave function, we can see this explicitly. So when we make a rotation on a state, then if we take a projection to the position representation, then that is just a rotation of the wave function. So you can think of it as the wave function being rotated in space, or you can also think of the coordinate system being rotated like that. So that's what we have. That's what, yeah. But it is not so simple when we have a spin state, because the spin state lives in spin space. It's a two-dimensional space. We have a spin half. So we cannot make a projection onto position eigenstate. So we have to stick to the spin space. So we cannot see this in explicitly. Okay, so we start with rotation in spin half space. And we have the Pauli matrices. And so as a convention, as usual, we choose the eigenvectors of Sz as our basis vectors. So we have up and down states that span the two-dimensional space. So then any spin state can be written as a linear combination of up and down states, like so. That is just a summary of all the matrices. So the Pauli matrices is then given by this here, I think you all know. So one of the important properties of this Pauli matrices is that if you take the square of it, then it's equal to 1. It's also Hermitian, and the determinant is equal to -1 and has a 0 trace. So these are some properties of the Pauli spin matrices. So these spin matrices can be derived from this commutation relation here. So given this commutation relations, we can term over this commutation relations of the spin operators. Then we can work out the operators for xx and sy, and that will give us then this Pauli matrices. So I have it worked out in the notes, I think. But I thought that you already know about this, so I did not go through this. Okay, so that's the basic Pauli matrices. So now we can apply the rotation operator in this spin space. So it's a two-dimensional Hilbert space. So then the rotation operator in this spin space is then given by, oops, what happened here? So always problem with that. Okay. So this the rotation operator in spin space is then given by this one here. Or we can write it in terms of the sigma. And I think we did this last time, so we worked out explicitly the form of this rotation operator simply by expanding the exponential in power series. And then we use the fact that sigma dot n this squared is equal to 1. Then we can work it out this series easily, so that becomes a cosine phi upon 2 times unit matrix minus I sine phi upon 2 times sigma dot n. So this one here. So if we then use the Pauli matrices, so this is the operator spin, the rotation operator here. So now we worked it out in the up and down states of the spin half. Then it just means that we replace the sigma with Pauli matrices, and we get this explicit expression for the rotation operator in 2 dimension. Yes. And then we apply this to figure out the eigenvectors of the spin half operator along an arbitrary axis. So there are several ways of doing this. So the most direct way of doing this is simply to work out what the spin operator is along some arbitrary axis, call it n. So if we have some axis z, x, y, I think, yes. So we take some axis n here, and I think it is called beta, and this is alpha m. Then we just form a dot product between the operator sigma and n, and use the Pauli matrices, and then gives me this 2x2 matrix. And just replace an x and y and z on this, so that nz is just cos beta, for example, and so on. So then we get this 2x2 matrix. And then all we have to do is just diagonalize this matrix. So that gives me 2 eigenvectors corresponding to the up with eigenvalue h bar 1, 2, and this one with a minus 1/2 h bar. So that's a direct way of figuring out the eigenvectors of the spin operator along an arbitrary axis. Just take the spin operator along that direction and then diagonalize the matrix. But there is a more interesting way of doing this, kind of more elegant, you might say. That is by using the rotation operator. So what we do is we start with spin up eigenstate, the z direction. So we start from this state here. So z plus, let us spin up. And then we rotate this state by angle beta around the y-axis. So we construct a rotated state. Let's call it z prime plus. So this is the rotation operator around the y-axis by angle beta. So now the state is rotated along this direction here. So this state, the z prime plus, is an eigenstate of the spin operator along the z prime. Yes, because we rotate that state. So we see here actually the connection between rotation in real space and the rotation in the spin space. So the rotation itself is in the real space, so that's a rotation by angle beta around the y-axis, and it induces a rotation in the spin space in this way here. So the rotation operator rotates the spin up state along the z-axis to another state along the z prime. Yeah. So if you want to know the eigenstate along n prime, along n, so this is our n here, then all we have to do is just do another rotation about the z-axis by angle alpha. So this is what we do here. So we continue rotating the state around the z-axis by angle alpha. So then we get what we want. So that would be the eigenstate of the spin operator along this n. So it's the n is equal to n. Yeah. So usually we define the positive angle to be anti-clockwise. This is a convention. So this is kind of nice way of constructing the eigenstate, the spin operator along an arbitrary axis. So let's work out and see that we get the same answer as we did by direct diagonalization. So let's first work out this operator here. That one there. So we have already worked out the explicit expression for the rotation operator. So if we make a rotation around y-axis, well, that means that nx and nz are equal to 0. Yes. So then we just plug in that nx and z equal to 0 and put in the right angle beta here. So we get this matrix. So that's the matrix representation of rotation operator around the y-axis by angle beta. And we do the same for the other rotation operator. That's a rotation by angle alpha around the z-axis. So in that case, then nx and ny are equal to 0. So we get this simple 2x2 matrix diagonal. And now we have to do is just multiply these two. And we operate it on the spin-up state. So these are the spin-up state. And we get this answer, which is what we found before by direct diagonalization. And we can do the same for the spin down. So we just start from the spin down and do similar kind of rotations. And you get this one here. Okay, so that's kind of repetition of what we did last time. So now I would like to verify that if we make a rotation of an arbitrary spin state, then the expectation values of the spin components do actually rotate in real space. So that's what we might expect. So let's do that. So what we want to show here is that if we start from some arbitrary state alpha, and let's say we make a rotation around the z-axis by angle phi, we choose rotation around the z-axis because that we choose the basis to be the eigenvectors from the sz, but we could have done it for any direction. So there is nothing special about this. It is quite general. So we have a new state alpha prime, which is a rotated spin state. Then we want to show that if we take the expectation value of Sx and Sy, so in the rotated state, so the prime here indicates that the state is rotated. So this we have here. Then that expectation value is really just a rotation of the expectation value of Sx and Sy in the old or in the original state. So that's like what we would expect. Physical consideration. Okay, so let's try to do that. So an exercise here. I have this also in the notes. We want to calculate prime. Like that. So that becomes alpha is rotated so that phi is x that's it. Alpha. So that's my prime. So now all we have to do is look at these operators here. So we want to calculate operator. So to do that, we just insert operator. So Sx is given by e to the power upon 2. Spin up, spin down, and then spin down. Spin up like that. So that's our Sx. We have like this. So the states up and down are eigenstate of Sz, so we can easily calculate this. Then we get h bar 1, 2. That gives me 5, 2. And we have operator, so that x to the left gives me into the 5, 2, because it's a spin down, so it's minus h bar 2, the eigenvalues. And we have this one here. Okay, so that's quite straightforward, just applying this operator on the states. So if we collect things together, all these terms, then we find that this is just h bar upon 2, and then I have the operator, which turns out to be Sx. And I have a cosine here. And I have I minus it's fine. So if you just work this out, that's just a couple of lines of algebra, then you get this expression here. Then we realize that this is just Sx, including the h bar 1, 2 cos, and this one here is the S minus this one. So then it becomes Sx cos phi minus Sy sine theta sine phi. So we see that if we take the expectation values of this in the state alpha, so we put this back here, and we put this back here, then we get what we want to show. So we get expectation value of Sx in the rotated state is equal to the expectation value of Sx in the original state, cos phi, 10 minus Sy phi, and similarly for the S1. Like this, yes. So we can write this as a matrix equation, and we realize that it's just what we have here. Oops. is just what we have here. So it's really rotation and xy plane of the component xx and sy, because these are just the rotation matrix, the dimension by angle phi around the z-axis. So that's nice to verify that it does indeed rotate the expectation values. If we look at the states, however, we find that there is something a bit peculiar. So the expectation values of the spin operators behaves very much like what we would expect from physical consideration, that it is rotated in real space. However, if we look at the spin state itself, it has a kind of peculiar property in that we make a rotation by 2 pi, the state does not return to itself. It acquires a minus sign. Yes. So we can see this more explicitly by looking at particular state, or not particular, but arbitrary states. I can look at the state alpha. So I call it C plus up and then C minus down. So this is an arbitrary state in the spin space. So now we make a rotation around z-axis. We don't have to do the rotation around the z-axis, but it is simpler. It is quite general. Then if we just use it here, then these two states are eigenstate of Sz, so then it's easy to calculate it. We just get 1 to C plus, and then we have 5.2 C minus down. So the peculiar thing is that if we plugged in phi equal to 2 pi, then we find that this rotated state is not equal to alpha, but rather equal to minus alpha. So it requires a minus sign because of the presence of this factor of half. So we will have to rotate by 4 pi in order to get back to the original state. Yeah. So this property has some consequences, we'll see later on. So let's illustrate the use of this rotation operator by considering the example of spin precession that we did earlier. So this is spin precession. So the Hamiltonian is quite simple. It's just omega time z like this, and omega here is the cyclotron frequency. You can put a minus sign there, but doesn't matter. So we start with some initial spin states. So we have some initial state. call it alpha. Then we know that at a later time, so we just apply our time evolution operator. So then we get then we make a t here, alpha, like this. So the interesting thing here is that here we consider a time-dependent problem. So we have some initial state alpha, and then we evolve it some time later, t later, with this Hamiltonian. But we can also think of it as a kind of rotation in spin space. If we think of this omega t as some angle, phi, then this is just equivalent to rotation of the spin state by angle phi, which is equal to omega t around the z-axis. So there is, so in a way, we have gotten rid of the time and replace it with angle. So we have this possibility of describing time-dependent phenomena, but without explicitly considering the time. Yes, because we can replace this omega t by the angle. So this may be just a coincidence, but so then we can just use our previous results. So if we look at the expectation value of this x component, this spin as a function of time, then it will be just given by expectation value, the initial expectation value, time cos phi, so now becomes times cos omega t minus s1 sine omega t, and that's same for the sy. Yeah. So this is the same result as we got for the rotation before. All we have to do is just replace phi with omega t, because it's exactly the same problem. Okay, so this is just one example. So I feel ready. Think, yeah. So now I would like to talk about the Euler rotations. So Euler rotations is Euler theorem tells us that if I have, or if I make rotations of a rigid body, rigid object, around an arbitrary axis by some angle, then it is possible to decompose this rotation into 3 successive rotations about some fixed axis. So this is the Euler theorem. It's always possible to rewrite any rotation as 3 successive rotations about some fixed axis. So we choose a Cartesian coordinate system, x, y, and z, then any rotation can be written as a product of successive rotations around the fixed Cartesian coordinate axis. So before we do that, we just mentioned here a few things about the rotation group. It is nothing very important maybe, but you just need to know what these are. So rotations evidently form a group, because if I multiply two rotations, like R1 and R2, for example, well, that will just give me another rotation. So one way to think about this is just if we replace R1 by R1 and R2 by some orthogonal matrices, then we multiply two orthogonal matrices, then we just get another orthogonal matrix. And so that also represents a rotation. Yeah. So we multiply two rotations, one rotation and then another rotation. Well, that is just equal to another rotation about some axis. Yeah. And obviously we have this associativity, and we have identity, which means there is no rotation. So that's the unit matrix. And we have an inverse, of course. Yeah, we make a rotation, and it's always possible to rotate back to the original position. So this set of orthogonal matrices then form a group. So this is called the SO3. So it's special orthogonal, and the 3 for the dimension, 3 dimension. So there's a name here. And I always say this, that we should be careful when we talked about inversion, because inversion is not a rotation. Yes, so one cannot have inversion by doing rotation. So inversion is a discrete operation. So it's not the same as making a rotation by 180. That's not the same. So if you make an inversion, the coordinate system changes from right-hand coordinate system to left-hand coordinate system. So that you cannot obtain by doing a rotation. So that's just an important point here. So inversion is something else. So if you include inversion in the group, so it's will be down, then you will get this group called O3. Anyway, that's not so crucial for our purpose.
Is inversion a parity transformation?
Yeah, that's right. So you change the coordinate from R to minus R. Yeah. And the point is that cannot be obtained by rotation. So rotation here means a rotation of a solid object, rigid body. Very much related to this orthogonal 3x3 orthogonal matrices is a set of 2x2 matrices, in which the elements can be complex. And so these are called the unitary unimodular matrices. It's called SU2. So S is for special unitary matrices of 2-dimensional. And it has the properties that it's unitary, so that U dagger U is equal to 1, and the determinant is equal to 1. So these are the basic properties of this SU2 matrices. So the most general SU2 matrix can be written in this way here. That's the most general form. So the A and the B are complex numbers. So they are usually called the Cayley-Klein parameters. and they fulfill these conditions that a squared plus b squared is equal to 1. So that then makes sure that it fulfills the definition of the SU2 matrices. So now if we make a comparison with our rotation matrices in the spin-half space, then we realize that we can identify these parameters A and B as the one we have here. So if we just make a comparison with the rotation matrix that we worked out before, then we realize that we can identify this parameters, the Cayley-Klein parameters A and B, as this cosine 512 minus and so on. Yes. So this indicates, or this shows that these SU2 matrices also represent rotation. So it's a two-dimensional version of rotation of the representation of the rotation operators. But then they must be related to the rotation of 3 dimensions, the SO3, because this A and B, this parameter, contains the information about the rotation. So we have nx, ny, and z, as well as the angle. So we know that that defines the rotation in 3 dimensions. So this SU2 matrices can actually represent rotation. So these are just the j equal to 1/2 representation of the rotation operator. So the thing to note is that the relationship between SU2 and SO3 is not one-to-one. So for a given rotation in real space, so that's represented by a matrix of SO3, this orthogonal matrix, there corresponds 2 elements of SU2. So there are 2 elements of SU2. So it is represented by or labeled by AB and minus A minus B. So these 2 SU2 matrices are different. So we have U AB is not the same as U minus A minus B. And you can see that explicitly in this equation here. They are different, but nevertheless, they correspond to the same rotation. So you have the same axis and the same angle correspond to in real space. So there is the connection between these two groups, SU2 and SU3, is not 1-to-1, but 1-to-2 or 2-to-1, depending on how you see this. Okay, maybe we should have a little break here. We have gone over 5 minutes. Okay, so before we have a break, maybe there are questions. Okay, so we don't have questions. We just continue. Maybe so let's see, it's 11. So maybe we start at 20 past there. So we meet again at 11. Okay, so let's continue. So just to summarize what we said earlier. So the rotation matrices in spin space, that is 2 by 2 rotation matrices that we worked out before, those are just the SU2 matrices. So they represent a rotation in a spin space. And also we can see explicitly the connection between rotation in the 2-dimensional spin space and the rotation in 3 dimension. So, so it's a 2 by 2 matrices, and they act on the 2-dimensional spin space, the up and down space. But at the same time, the parameters that define the matrices, so those are the parameters here, the nx, ny, nz, and the phi, they define a rotation in 3 dimension, so in real space. Yes, so this then gives the connection between the rotation in real space, 3-dimensional real space, and the rotation in the Hilbert space of the spin half states, which is a 2-dimensional space. Okay, so the next thing I would like to do is to show its Euler rotations. So Euler theorem says that any rotation, so let me write it down. So any rotation of a rigid body can be decomposed or rewritten into 3 successive rotations about some fixed axes. So some fixed axes, we mean here some Cartesian coordinate systems. So how do we see this? There is a simple way of showing this or proving this. So first of all, it is important to realize that this is a rotation of a rigid body. Yes? So we are not allowed to distort the object. It's a rigid body. So let's take the rigid body to be a set of Cartesian coordinates. So we have x, y, and z, and they are fixed. They are rigid. So now we make a rotation, some arbitrary rotation, and let's just focus on the z-axis. So the z-axis is now rotated. Wait a second, what am I doing here? Okay, so the z-axis is now rotated to z prime. So we have a rotation, and we don't pay much attention for the moment on the x prime and the y prime axis. So they are somewhere, they are perpendicular to the z prime, so we just concentrate on the z prime axis. So this is what happens when we do this rotation. Yes. So we want to show that we can do these rotations by performing 3 successive rotations around the fixed axis, x, y, and z axis. Okay, so to do this, so let's first try to return or realign the z prime to the z axis, the original axis. So what we can do is first we rotate the z prime around the z-axis by minus alpha. So minus here means clockwise. So we just rotate it like this by angle alpha. So then we end up here. Yes. So the z prime axis is now on the xz plane as we rotate it by angle minus alpha. And then we make another rotation. So that's the second step here. So we rotate this z prime around the y-axis by angle minus beta, because it's a clockwise rotation. So we do this rotation here. So then we align the z and the z prime axis, so they're back to the original positions, the z prime. So we have not talked about the x prime and the y prime axis, but we know that the x prime and the y prime axis must be perpendicular to the z prime, so it must be in the same plane. So for example, it could be like this. And they're in the same plane as the xy plane. Yes, it has to be, because the z prime is perpendicular to the x prime and y prime axis. So then all we have to do is to return the prime axis to the original axis, is make another rotation, the final rotation around the z axis by some angle, so that the x prime and the y prime coincide with the x and y. So that's the proof. Yes, we have three steps. First, rotation around z-axis by angle alpha, and rotation by beta or minus beta around the y-axis, and the final rotation around the z-axis. So any rotation can be written as three successive rotations. So to be more precise, we have minus alpha and minus beta instead of alpha and beta. So we have this first two rotations by minus alpha and then by minus beta, and then by some angle minus gamma. See? So these three successive rotations return the prime axis to the original axis. But what we want is to rotate the original axis to the prime axis. But these are just the inverse rotation. Yes. So we take the inverse rotation, and that is then just given by this here. So, and that follows from the fact that if I have R1, R2, R3 minus 1, so that is equal to R3 minus 1, R2 minus 1, R1 minus 1, and R alpha minus 1 is equal to R minus alpha. So that's the proof. Yes. So any rotation can be written as three successive rotations about the fixed axis. So the choice of this axis here is kind of arbitrary. There are other possibilities of doing these rotations. It doesn't have to be z, y, and z. So we have chosen this particular rotations, first along the z, and then along the y, and then along the z again. So there's a reason for doing this, because the rotation about the z-axis is easy, because we choose our basis to be the eigenstates along the z-axis, usually. That's our convention. So then, any arbitrary rotation, when it is represented in this way, as three successive rotations about Z, Y, and then Z again, all we have to worry about is the rotation about the Y-axis. Because the rotation about the Z-axis is easy to perform, because all the basis function, the basis vectors are chosen to be along the Z-axis. So this is the usefulness of the Euler rotation. So instead of figuring out rotation for any given rotation, so that's a quite complicated thing to do. We just have to worry about rotation about the y-axis. So this is the Euler rotation, and we will come back to this later. So we can then rewrite the rotation matrix, rotation matrices, in terms of the Euler angle. Yeah. So we have this 3 successive rotations around z-axis, on the y-axis, and the z-axis again, with angle gamma, beta, and alpha. So we just have to replace each of these with a given rotation matrices and multiply them out. Then we get this representation in terms of Euler angle. So this is the representation of the rotation matrix in terms of the Euler angles. So these Euler angles, alpha, beta, and gamma, can be related to these parameters that defines the direction n and the rotation angle phi. So that is just a mathematical problem, but it's a well-defined equation we have here. So we have 3 unknowns defining this direction and the angle phi, and we also have 3 unknowns, the angle alpha, beta, and gamma, which can be solved. So they're well defined. What is not well defined is the choice of the axis. So we can we could have chosen different set of rotations instead of z, y, and z. We could have chosen a different paths to speak, and get the same rotation in the end. So the reason that we choose this is because we choose the z-axis to define our basis vectors. Okay, so the next thing is a bit of a digression. So I'm just following the textbook here of Sakurai. So this topic about density operators of pure and mixed ensemble are not really related to angular momentum, but the examples taken from the angular momentum, like for example for spins, kind of illustrative to describe this formulation of density operators. So the topic itself is quite independent of angular momentum, so it's a kind of digression here. So what is it about? So usually when we have a quantum system, we describe it by a state vector. So we characterize this quantum system by a state vector. Let's call it psi here. And if we want to know the expectation value of some observable, which is represented by some operator, let's say A, then what we do is we take the expectation value. So what do I have here? Wait a second. Okay. Yeah. So we have an operator A representing some observable, and we want to calculate the expectation value. So then what we can do is we insert a complete set of states like this, where let's get here, where the states AI are eigenvectors of A, operator A. So then this becomes I here, and I have psi I psi, so that is square. So this coefficients, the overlap of the state I with the state psi, taking the square of it, gives us the probability, or given the weight of finding this eigenvalue AI. Yes. This is the expectation value of an operator in the given state psi. So this is usually what we have. We have a set of identical quantum systems, and we make measurements represented by some operator A, and the expectation value is then given by this expression here. So a single measurement, of course, will just give us particular eigenvalue of the operator A. So we have to make many measurements to compute the expectation value. So that is fine if we have all the quantum systems in the same state. In this case, the state psi. So let's say we have particles like electrons, and we're just looking at the spin state. And so we have these electrons, all these electrons in, let's say, spin up state. And then we can calculate the expectation value of some operators, known as spin operators, in this spin up state. So that's one example. But in general, we might have a situation where we have lots of particles which can be in different states. So we have, in the case of spin states, we could have, for example, let's say a third of the particles in spin up state along the z direction, a third in the spin down states, the z direction, and the remaining 1/3 could be the spin up state in the x direction, or some other arbitrary directions. So we could have a situation in which the particles are in different states. So such a system is then called an ensemble, for kind of obvious reason, because we have an ensemble of particles in different states. So the question is then, if you want to make a measurement on this system, what kind of results do we get then? So we have this operator A, let's say, representing some observable, and we have this ensemble. What would be the expectation value that we get from this ensemble? So this situation was considered by von Neumann a long time ago. I think it was in 1927, not long after beginning of quantum mechanics, actually. So he wrote, it's called this ensemble average. This is the ensemble average. This is the kind of analog of the expectation value. It's called the ensemble average. So he said then that this is equal to sum over I, and I will explain what this means later. I have some weight here. Like this. So if the systems are in different states, so this I here labeled different states, and M is just the number of these different states, yes, in the ensemble. So this means that omega I tells us the fraction of particles in state psi I. So in the case of the spin half, this could be the fraction of particles in spin up state, let's say, along the z direction or along some arbitrary direction. So the ensemble average is then given by this expression here. So that makes sense because these are just a statistical weight. Yes, so this is just statistical weight. Statistical weighting. So each expectation value is then weighted by the fraction of the particles in that state. So it makes sense, yes. So this weight, of course, must be positive and less than 1 because it's a fraction. So total the sum of this weight must be equal to 1. So this seems to be kind of obvious. There's nothing strange about this. So what von Neumann did is that he went further and analyzed these expressions in the following way. So we write this ensemble average. So let me write again. I am weight so we can then insert a complete set of states here, for example, where AI is the JAS, are the eigenstates of A. Then we get like we had before. So that would be the probability of finding the state psi I in the eigenstate AJ. e.g. like this. So that's what we had before. So for the expectation value of the operator A in the state psi, here will be state psi I. And one can rewrite this in the following way. So we have set I to M, and we have J here. So we can open this AJ, AJ. So this whole thing is just that one. Then we realized that we can rewrite this expression in the following way. AJ, put it outside, and bring in the sum over the I. Like this. We have the operator A. Like that. So we recall that if I have an operator A, we can always write this as a sum over J of the eigenvalue and the states, like this. Yes. So I think I made a mistake here. There should be, let me see. What am I doing here? A, J, J, I, yeah. So this thing here is just AJ and AJ like this. So I have replaced that with that thing. So that's the same as replacing the A with this expression here, yes? So the interesting thing about this is then, this is in the form of a trace. So we have trace of what we call a density matrix, so density operator, and A, like that. So this whole thing here, we call it psi A, like that. So the density operator is given by M to weight psi I, like this. So one important point about this density operator is that the states psi, so psi I, yeah, need not be orthogonal. It not be orthogonal. So if we take an example of a spin half, particles, I could have any state. So I could have a spin arm like this along the z-axis. Let me label it with a axis like that. And I could have a state along some arbitrary axis. Say spin up or spin down. So these states are not orthonormal. So these states are arbitrary as long as they span the same Hilbert space. So that is an important point about this density operator, that the states which constitute density operator need not be orthogonal. They can be any states defined in the Hilbert space, of course, of the system. So, and the number m here, so the number of possible states, can be anything. It can be very. It has nothing to do with the size of the Hilbert space. So this can be is arbitrary. So it can be very large, can be very small. It depends on the ensemble. So if we have a spin half particles, so the Hilbert space is two-dimensional, but this m here can be anything, can be 100, can be 1,000, whatever. So obviously then the states cannot possibly be orthogonal if we have more than two. So the states can be any state defined in the Hilbert space of the system. And another interesting thing about this ensemble average is that it's a trace. So then we take the trace, it is independent of the choice of the basis. So it is independent of the choice of the basis of base vectors. So in this derivation here, we have chosen these states aj to be the eigenvectors of A, but because this is in the form of a trace, then we don't have to use the eigenvectors of A when we calculate this ensemble average. It can be any base vectors. So this trace here, this ensemble average, is independent of the eigenvectors of A in the sense that it is a trace. We can choose other base vectors. It doesn't mean that the value of this ensemble average is independent of the eigenvectors of A, because of course the operator A can be written in this way, so that of course depends on the eigenvectors and the eigenvalues. But this particular form of the trace is independent of the eigenvectors of A, so we can choose other basis vectors to calculate this ensemble average. So this is the general formulation of computing an ensemble average of an operator when we have what is called the mixed system or mixed states instead of pure ensemble. So in the case of pure ensemble, all the particles are in the same state, but in the case of a mixed ensemble, the particles can be in different states. So the weight of the ensemble is given by this Wi. Yeah, that tells us the fraction of the particles in the state psi I. So one important thing about this is, I think you should know, is that these coefficients, this or this weight here, W, is a statistical weight. It's a statistical weight. So we should not confuse this with coefficients in the expansion of a wave function in certain base factors. Yeah. So if we have a state psi, we can expand this in some base factors, like phi I, and we have this coefficient Ci. So this Ci here is not related to this statistical weight. So W, yes, Wi is just a weight. It's a statistical weight. It's a real positive number. Yes. Whereas this is a coefficient, which can be complex, and there is a phase relations between the different coefficients. So let's try to illustrate this in the case of a spin half particles. So we can have a pure ensemble. So pure ensemble means that all the particles are in the same state. So let's choose a state psi. Go to half plus like this. So this is, as you might notice, these are just the spin up state in the x direction. Yes. So this is an eigenstate of the spin up of Sx in the so that would give us the h bar of 2 psi. Yes. So this is a pure ensemble because all particles are in this state. That's the spin up state in the x direction. So in the case of mixed ensemble, so this is just an example. So we have, let's say we have a mixed ensemble. So the mixed ensemble is characterized by the density operators. Density operators is very important because that characterizes the ensemble. So let's say that we have half of the particles in the spin up state along the z direction, and the other half in the spin down states, like this. So, so this tells us that half of the particles in the spin up and the other half in the spin down. So if we make a measurements along the z direction, then actually we will get same results because we consider this pure ensemble. If we make measurements along the z direction, then half of the time we will get spin up, and half of the other time we get spin down because we have this equal coefficients for the state for the pure ensemble. And that is also the same with the mixed ensemble because there is half of the particles in the spin up and the other half in the spin down. So obviously, if we make measurements along the z direction, then we will discover that half of the particle will be in a spin up state and the other will be the spin down. So there's no difference between these two ensembles if we make measurements along the z direction. However, if we make measurements now along the x direction, then it will be different Yes. So in the case of the pure ensembler, we always find the particles to be in the spin-up state because this is an eigenstate of the of Sx in the, so that's the spin-up eigenstate in the x direction. So then all the particles will be in these states, and also then we will always find a spin-up results if we make a measurements along the x direction. But in the case of the mixed ensembler, we will get still half and half. Yes. So we calculate the ensemble average using this density operator for Sx. So we calculate the ensemble of Sx. So that will be the trace of rho Sx. Then it's kind of obvious here because each of these will give us a 50-50% of Sx. So we will find that half of the particles will be in the spin up and the other half will be in the spin down. Yes. We make a measurement along the x direction. So we get different results between these two ensembles. So this is illustrate the difference between the pure and the mixed ensemble. So if we just make measurements along the z direction, then we cannot tell the difference between these two. But if we make measurements along the x direction, then we'll discover that these two systems are different. Okay, so that is just an illustration to show that the pure ensembler and mixed ensembler are fundamentally different. Yes, because in the one case, you have all the particles in just one particular state, whereas in the mixed ensembler, the particles can be in different states. Okay, so maybe we can stop here. We are already over 12 o'clock. So are there questions so far?
Yes, I have a question. It's just that how can you say that this when you say pure ensemble up there, how can it represent multiple particles pointing in the Sx direction? So it could be 2, 3, 10. Is that what you're saying? This pure ensemble?
Mm-hmm. So your question is that how we can tell, or I mean, you prepare the system.
Okay.
So it's not something that it's something that you create. Yes. So you prepare that to have all the particles in a certain state. So you have a, let's say, by using some magnetic field, in the case of spin, you can create an ensemble in which a certain fraction is in a certain state, spin-up state, let's say, in the z direction, and then you turn your magnetic field and you create another states. So you can have a kind of filter. Yes. So you actually prepare the system. And if you don't know the system, then it is random. Yes, then you have a random assembler. So in general, if you just have some particles from some oven, let's say, then you should treat it as a random ensemble. And the particles can be in any spin state.
Okay. Thank you.
Yeah.
I ask a question about the exam?
Yes.
So on Time Edit, it seems like you booked the Victoria Stadium.
Yes. So of course that cannot be done anymore. So I have actually talked to the administrator, and it is possible to have a Zoom exam. So we
Okay.
will have like a normal exam, but via Zoom.
Yeah.
Yeah.
Okay.
So, you are not allowed to use textbooks or notes. It's just like a normal exam.
Okay, so we will have the camera on and
Yeah.
okay.
So last year I had an open book exam that we just have a take home exam when you have to do this within a certain amount of time. But then we'll have to have an oral exam afterwards. So this time you just have an exam like normal, no oral exams.
But will you then have a formula sheet or?
So normally I will give this formula in the exams. Yes, I don't have a sheet, but I will have the necessary formulas in the problems.
Yeah. Okay.
So normally you don't have to memorize too many things. Of course, you should know some basic things, like I don't know, like let's say rotation operator. You should know, yes, but not some complicated formulas like what is the representation of the rotation operator in the spin half space, for example. That you do not need to memorize. Yeah.
But you should know this D.N or.
Yeah, the D dot N. What do you mean?
Yeah, or was that what you meant with the rotation operator?
Yes. So you should know the general formula. Yes. So I would say you do not need to memorize things. Yes.
Yeah.
Except for some very, very basic things. Okay.
Can I also ask about the exam?
Yes.
Will there be more information later on about practicalities? Because so far I've only had the oral exam and take-home exam during the pandemic. So
yeah,
I'm not so familiar with this Zoom setup for the written exam. Will there be instructions for this?
Yeah, there will be some instructions for this. Yes. So I also never done this myself, so I will have to ask the administrator about how this is actually done. And also I will ask my colleagues who have done this before. But it seems to be quite possible to do this. And we are kind of expected to do it when it is possible.
Okay.
Because we are not supposed to deviate too much from the original, we say, course description. So we try to be as close as possible to the course. Yeah.
Okay. Yeah. Thanks.
Yeah. So basically, we'll have a normal exam, but via Zoom. So there will be some camera, I guess.
So should one film the desk and the computer screen simultaneously somehow? Do you need several cameras?
I guess you need at least one camera, right? To show that you working on your own and you don't have books in front of you. Yeah. So yeah, I guess you will need to, because you will have to read the exam problems, which I will upload into Canvas. And then you need a camera I guess that shows that you are working on your own. I think that's I'm just imagining that's
Yeah,
what's happened. Yeah, but I will have to ask people who have done this exactly how they do this.
okay. Yeah, thanks.
Yeah, I'm very sorry about this, but this is not something I can control. So I hope it is not too much pressure and too much on you. Yeah, so I will probably give you some extra time also because you will have to convert your well, you have to scan, I guess, your answers, and then you have to send it via Canvas.
So should we still write on paper then?
Yes.
So
yes.
not in LaTeX.
No. That will take too much time, no?
Yeah, okay.
Because you have a certain, you have 5 hours, so it's not possible, I think.
Yeah,
So
okay.
you just write it down on a piece of paper and then you scan it,
Yeah, okay.
PDF file, and then you upload it to Canvas. So I guess that may take like if you have half an hour or so, that's it. Should work, hopefully.
Yeah, okay.
You might like to practice a little bit.
Yeah, that's probably a good idea.
So you know that it works. Okay, are there any more questions? And yeah, I have also uploaded the solutions to the exercise problems, if you have not noticed it. I usually do this after the exercise classes. Okay. So there is one more question here. Okay, then I guess Edgar's here. We can maybe discuss this separately. Yes. Okay, so let's then meet again on, I think it's on Friday. Yes. Okay. So bye bye.
Hi.